this whole thing has a history. I was preparing my lecture for FFT, and I will show you why suddenly came the idea of the generalized subband decomposition. So this is the whole outline. I may not be able to go through all of it because I was told in 45 minutes they will stop taping me. Is that right? Or anyway, something will happen. So I'll go through quickly the basic idea, and the whole thing came from that subband discrete transform, because I found a way to generalize DFT. That left to DCT, then a lot of application. I'll very quickly go through the application. And it's basically about 3 PhD students, starting with the first one. Okay. Polyphase decomposition was proposed by a gentleman, Frenchman called Maurice Bellinger. And that is, you may not follow the mathematics, but see if I have a physical. There's the basic idea. If I have a sequence, for example, you keep the even samples, you divide into 2, and the odd samples. This is the way he created the polyphase decomposition, and you can do 3-band. So this is the basic idea. Don't forget about the Z is the advanced operator. That has no meaning, but basically you are down sampling by factor of 2. So the even samples are x0 n, and the odd sample x1 n. And this is the physical reasoning behind the 2-band case. So you can do 3-band as shown here. You give every third sample, so you're basically dividing the sequence into 3 subsequences. And so when I was preparing the idea, this is the 3-band case. Then you can generalize to m-band. Okay? So if you take the Z transform of all of them, oops, this is basically the mathematics behind the relation between the original Z transform and the Z transform of the subsequences. Okay? And this is again writing mathematically the polyphase decomposition. And so my idea was, what happens if this is the physical interpretation, and this is the 2-band case, how to get back the original sequence from the subsequences. And then you can get back from m subband the original sequence, except they'll be delayed by m samples because you're putting delay blocks. Okay? So basically this sequence is a delayed version of the input sequence, as I showed in the previous diagram. So the structural advanced subband is a generalization of polyphase. When you do polyphase decomposition, the subsequences are all correlated. There is no frequency separation between the subsequences. So we came up with the idea putting a filter before you do this decomposition, and that we call the structural subband. So let's take a sequence of 8 samples, n equal to 0 to 7. So polyphase decomposition, you're keeping the even samples and the odd samples. So the 4 even samples, 4 odd samples. And the structural subband, we are putting a matrix T between the polyphase decomposition and the Z transform the subsequences. If T is an identity matrix, you have the standard polyphase. Okay? So the structural subband, and we call the subfunction the. I hope you are following me. Are you following me? If not, say you are following me, please. Okay, good. So basically, if I put an arbitrary T matrix, M by M non-singular, we can call a subband decomposition. And let me just see if I finish. So then you can get back the original subsequences by the inverse to the subband subsequences. I don't know why I put all this mathematics. I have difficulty following it. So this is basically you're doing called analysis filter back. Original polyphase T is an identity matrix, but in generalized subband we put an arbitrary matrix which is invertible, and by choice of the that matrix you can get different kind of subband decomposition. So then you can recover them by doing the inverse transformation. I should have a diagram here. So basically first you're downsampling to get the subsequences, then you're upsampling, and you can get back the original sequence provided all of them are perfect. Okay? And the sequence you recovered is delayed because of this Sorry, this light is not working. So the way we are generating them, we analysis filter bank here, and this is the synthesis filter bank. This is the analysis filter bank. And then we downsample, we get the subsequent there, which we call structural subband decomposition. By the way, when you start writing papers, some of you are graduate students here. How many graduate students? Okay. When you write paper, always create a new word. And reviewers don't have any idea what you're doing, your paper will get accepted. So I'm very good in that. So structural subband, I thought it was a nice decomposition. Anyway, so this is how we generalize the polyphase decomposition. But most interesting thing is the application. I hope you got the idea what we are doing. Okay, so how we created the subband decomposition depends on the subband matrix. And you have a choice. And so the simplest one is DFT. So if you have a 4x4 DFT matrix, so this is what you get. And the advantage of DFT, you're not doing any multiplication. And so this is how the magnitude response for the DFT. And they're all equal. See how you're separating the frequency band. Because you can see each of the subband have a frequency response like a low pass, a band pass, and a high pass. And then you can use Hadamard matrix. The main advantage of that, you're not using a multiplication, but you don't have much physical separations between the subbands and frequency separation. So here the Hadamard, the problem with Hadamard, you can see the frequency response is not as good as FFT, but you can still get some. Depending on application, you decide what matrix to choose, okay? So one of the applications I'll show you is subband discrete transform. As I told you, the idea came to me when I was preparing my lecture for FFT. And I was preparing my lecture notes at home. And FFT basically divide odd and even, or divide by half. First half gives you one shorter DFT, second half gives, and you keep on doing it until you come to the 2x2. That's the basic idea between. And many people in DSP will call them divide and conquer approach. So when I was preparing, I said, what happens if I add and subtract? I can get back the original sequence from the adding means you're doing low pass filtering, subtracting you are doing high pass. And that led to a whole class. So the first of one we called is, which one do I use? Okay. Subband discrete DFT. Then we applied to DCT, and I'll show you some applications. Okay. I should not have done, there's too much math here. This is in trouble, by the way, Prabhu. Let me see, I have a picture. Oh, here. So this is, you have a M-band decomposition, and you're getting sequence of length p. They are p-point DFT, and this is the notation I've used for computing DFT of a shorter sequence. And you combine them, and that is the general idea of subband DFT. Okay? So here is for the 2x2, and this is the general Cooley-Tukey approach, divide by 2, odd and even, and that's how they got their FFT algorithm, Cooley-Tukey. Then we put a matrix T, so we generalize that to subband DFT, and by choosing T appropriately, you can do a lot of novel applications. And one of the basic ideas was, if I create a T, I divide up into separate frequency responses with little overlap. If some sequences have frequency contact in one band, I can neglect the other band. So I can get a faster DFT, which is an approximation to the original DFT. But for many applications, high frequency energies so little, it doesn't really matter. And I'll show you the application we got from the improving the JPEG compression scheme. Okay. So if the signal is a priori band limited to a solar frequency range, you can simply downsample by a factor of n only the first sequence and get rid of all the other. So you have an approximation DFT. Okay? And one of the applications I proposed to German military, actually. So if you're interested, I'll tell you what we tell them. But if the signal is not strictly band limited, you have some aliasing, but some cases aliasing effect may not be that significant. Okay? So if one band in an M band is dominant, you can get rid of M-1 branches. So for example, for an 8-band analysis, you need to compute 40% of the Kuritoki FFT, computed time. So you're getting a faster result, but their approximation to original DFT. Okay. So here I'm showing physically with a Hadamard transform R4, we dropped out 3. So basically we're getting so I put a delta, so what do you call it, wiggle on top to show it's an approximation. Okay. Okay. So here's the it's a 2-band using Hadamard transform. So you can get back the original sequence this way because you are doing it. If I see, since the Hadamard transform is just add and subtract 2 by 2. So top one you see I said subscript L, that means they're low frequency, and bottom one I put subscript A, they're high frequency. So I can remove that lower band if most of the signal energy is the low band. Okay? So anyway, so here's the subband DCT. This is the original DCT of length n. We can do the same thing like DFT. So this is the subband processing. It's still getting the original sequence back. Now you can write the DCT sequence as part of 2 subsequences. And this one, so you put a bar on top. So this is not strictly a DCT. I'll show you what the difference between, this is of the half the sequences. And this is, again, not the strictly discrete sine transform, it's only half of. So next slide should show you the difference. So this is the original DCT of the half the sequences, and we have a 0 here. That's why I have a bar here. Okay, so C sub 0K is the n over 2 point DFT of the approximated B0n, which is the low frequency signal. Okay, and this is of the high frequency. V1 of n is the high frequency part, and S1K is the n over 2 point DST of the high frequency signal. And in most applications, I'll show you, I can neglect that if signal is mostly low frequencies. Okay. So this is what we call subband DCT, and we can keep on doing it until we have a 2 by 2, as long as the original sequence is a multiple of 2. Okay, the subsequence of length 2. Okay, so exploiting the spectral contents, we can develop a very efficient DCT algorithm, and we apply the image compression as one of the applications. So if original sequence has most of the energy in the low frequencies, okay, so we can get approximately CQ by discarding all terms which are associated with high frequencies. So this is our approximation. As you can see, we are getting rid of the second half, and we can of course extend this to higher dimensions. Okay, idea is very simple. And then we apply to image compression, and I'll show you the color version. So type 1, we keep the Y component, and UV we quantize. Then type 2, those of it's not that important, but these are technically what is done in JPEG. Okay. Can you get the lights? This is an image many people will not use because it has a lot of high frequency. Basically, I want you to compare. This is the original sequence compressed of compression ratio of 50. And you can see when you do the standard DCT, you start seeing blocking artifact, which will be more visible in the next slide. And in subband DCT, same compression ratio, You can start seeing some blocking artifact here, but I believe the next one. Okay, now you see the blocking artifact. Compression ratio of 100. You can see the blocks, and this is our. You don't see the blocking artifact. So when I saw this, we applied for a patent. We got it, and then I think next one is also interesting. This is another good example. This has more color. The other one had more textures. And so compression ratio of 50, and this is our approach. You start seeing some blocking artifact here, and it'll be more visible next one. Oops. Here you can see the blocking artifact, and there our approach, same compression ratio. We got a patent. Unfortunately, JPEG was going out of business, and they went to Wavlet. And getting a standard, you have to have a company behind you. I could get any company, because Hewlett-Packard was pushing Wavlet. So that is the standard now for image compression. But anyway, we tried.
What do you mean by blocking artifact?
Because you're doing 8 by 8 block and compressing. So obviously you'll have some, because you're getting rid of some sequences. So if you take 8 by 8, when you compress, you're not getting the original sequence. So that's why you start, and if there's a big change in frequencies where you're doing it from block to block, you start seeing blocks. Okay? Okay, thank you. Then we applied to filter design, and I'm going to not show you all the mathematics behind. And show how to design more efficiently. And the reason I want to bring it out, this slide, is also, many years ago I did some work with a friend from Finland we call interpolated FIR filter. And that one, by the way, if you get MATLAB, they have incorporated a command called IFIR. That's our work. And also National Instruments in their LabVIEW has adopted this IFR. You get a very efficient filter, FIR filter, by decomposing as a cascade of 2 blocks. And first blocks have very few samples, and second block interpolates the missing samples. And you can get exact reconstruction, but it is more efficient than designing the FIR filter directly. And so we have a series of work going on, including adaptive filtering. I saw somewhere Matthews. Where are you? Oh, because we also apply to adaptive filtering. So any of this branch basically is the basic idea of interpolating, but this is a more general case because you're now getting exact FIR filter. And the IFR is an approximation. And so basically here, for narrowband FIR filter, we can drop some branches, and I think I have some examples, and you can very computationally efficient, and you can go directly into computer and design them using optimization. So here I'm showing how you can save number of multipliers if you have a symmetric impulse response. So this is how you realize more efficiently. Okay. So I'll show you some design using this concept, and both of them we get very good results with a lot more faster than direct design. In the one branch, we design each branch using a least square minimization or a minimax approach like Remez. And other one we use frequency sampling method to get the filter. So you are directly designed on the structure rather than taking the original FIR filter and optimizing, which is standard method. Are you following me? Originally you have all the taps, but here we're separating, and we could design one branch at a time, and you can keep on doing it, and it's much faster. Because when you optimize using any optimization, it's typically square of the number of variables, I think, I vaguely remember. Okay? And I think I may have actual computer time. So this is the parallel FIR structure, and this is how we're designing cascade of 2 filters. So in the first case, we determine only the n over 2, you're doing an M-band decomposition, And so each sparse filter you're designing one at a time. So you first design the dominant band, then use the other band, you keep on going back and forth. And it turns out to be much faster than directly designing, because shorter length you have optimization algorithm converges much faster. And the least square, standard least square optimization, you take samples of the amplitude response, and then you design what subband you want. GK is fixed. You're basically putting the FK, which are the subband decomposition. Okay. And so this is how you design. So you minimize the desired response to H sub D, and H halta is the one you're designing. So HD tilde is your design objective, and this is the subband approach. So GK depends on what subband matrix you're using, okay? And that is given, you cannot change. But FK is the one you're going to computer to design. Okay, so it minimizes results in all coefficients of Fk, from which you can get the impulse response, and the computation complexity of a modified least square is smaller by a factor of 1 over m compared to direct least square method. Okay. So here's an example, linear phase filter, FR length 128. We use a 8-band decomposition. It's a very narrow band. Pass band is 0.02 pi, stop band 0.45, and we gain response using a least square approach. Here is our filter, okay? We met the spec, but much faster. And then I'm showing the same thing with the minimax, which is like an MS-stack algorithm or Parks-McClellan type algorithm. So the filter we're designing is a bandpass filter. Pass band is 0.15 pi and 0.16 pi. So the bandwidth is from 0.15 pi to 0.16 pi, and stop band is at the low frequency 0.1 pi and high frequency 0.21 pi. And we assume equal weight in pass band and stop band. Then we apply the 8-band decomposition. So here's the one we designed. And one thing you may or may not notice, I have to point out, why are these coming? Because these are the subbands where they overlap, okay? And in fact, we have a paper with Tapio Saramaki. He showed you can get nearly optimum filter using a 2-band Hadamard matrix decomposition. It's a paper in circuit transaction. So we're applying minimax to smaller size subfilters. And frequency sampling is an old method which not many people use, but we got very good results using the FIR structure, parallel FIR filter. So here is a half-band FIR filter, pass band ripple 0.0013, stop band, use a 4-band decomposition. So this is our method, okay? So I'm showing the subband, some we have used very efficiently. These are all published work. We're happy to. Then you can use for efficient decimeter interpolators, so I'm going to ignore that. Normal FR adaptive filter use the whole FR structure, and since all the taps are correlated, it's not that easy. But by subband decomposition, the subband filter we can adapt independently, and since they're shorter length, adaptation is much faster than doing the whole thing. And then other approach is by choosing this matrix T, I can decorrelate the signals. If I do directly a FIR filter, I don't have any control. And this way we get much better result. And so here, by fixed universe transform, then we do sparse adaptive subfiltering. Mariani Petraglia's work. And for large M, we found recursive DFT, DCT are computationally more efficient than implement the transform T, than the FFT. And for small values of M, fast, non-recursive algorithm. Actually, we never applied to recursive least square. You may be interested, because I think it'll be much better because you're using a shorter matrix. Anyway, these are all the mathematics you can forget. And choice of transform T with good frequency selection decreases the correlation between transform signal, which can be used to obtain a significant improvement in the convergence speed of element for colored input signals. And we found either DFT or DCT quite useful. And since we are restricting each subfilter to a frequency subband, we can increase the speed of convergence. Okay. And then also, one of the ideas, in fact, we did have a conference paper, and original work was done. God, I keep getting old, remember the name. When you're doing adaptive filtering, suddenly one tap may fail. You cannot change it. So his idea was we adapt the other filters to get as close as possible to the original solution. And since original FR filter, all the taps are related, he didn't get very good result. And we showed by using subband decomposition, we have a conference paper we never published in journal to show the improvement you get using. And the basic idea was that when you have a satellite in adaptive filtering, you have no control. So our idea, if I have subband filter, if one subband didn't work, we switch automatically, because we can have the final output connected by switches, so we can switch them around. We got, anyway, that was the paper. So, okay, so here's we actually applied to real signals. And I had this gentleman from Germany, I'm trying to remember, he had actual data from the post office. So these are his data. So a subband adaptive line enhancer, input is a single sinusoid amplitude plus Gaussian noise, a variance 0.525 or a signal to noise ratio 3 dB. We chose length 128, 8 band, P equal to 16, and for the subband matrix we choose DCT, L equal to 8, DFT, L equal to 4, and we updated using LMS each subband. Then we estimate the power spectra using an average pedogram of 16 data blocks. In the DCT, we kept 2 out of 8, DFT, 1 out of 8. Okay. And both DC number of operations for ALE was about 1/4 than required in the standard ALE. And you can also get further saving when you use a frequency estimate of the input sequence is required. So here is our result, and I'm trying to see whether you can. Unfortunately, this I copied from the journal paper, so quality is not very good. Oh, the solid one is this one. Here's the frequency you are trying to estimate, and this is the noise level. And convention FR, I don't know whether I can see which one is which in this diagram. But basically, these peaks came because of the subband, but we're still below the noise level. So we could estimate the sinusoid very accurately using subband decomposition and much faster. Okay, as I mentioned, you'll see some minor peaks due to band removals, and many applications this may. And we have used this for acoustic. This is the echo cancellation. We had real data from German post office. I think that's the last one.